Hello, welcome to another video session of thermodynamics. In this video, I'm going to explain how the first law of thermodynamics is used to solve problems. Or in this problem, it's a very simple problem. We're going to see how the first law of thermodynamics is directly used to solve this kind of a simple problem. So let's see what our problem is. Share. Video. I will see the problem on the screen. And this problem, we are asked to find the boundary work. Let's read the problem first. A piston cylinder device contains 0.085 cubic meters of air at 400 kilopascal in 67 degrees Celsius. Heat is transferred to the air in the amount of 45 kilojoules. As the air expands, as the air expands isothermally. So when heat is transferred to the piston cylinder device, the air expands isothermally. So let's see what isothermal process is later on. Determine the amount of boundary work done during the process. Very simple, straightforward problem. But let's see how can this be solved. This kind of this we solve step by step. Now, my first step is to draw a figure that represents the physics of the problem and also that links all the data into the problem. So it gives us a visual aid for the problem. So I draw a piston cylinder device with a very simple piston and the cylinder. So this rectangular section is a cylinder, and this is the piston. And the air is contained inside. Air is here. And now what happened is at the beginning, we say the volume 1. So this is state 1. We name that as state 1, the first instant of the system. The states are defined by properties. So the properties that define this state is volume 0.085 cubic meters, and it is also defined by pressure P1 400 kilopascal, and then also the temperature 67 degrees Celsius. So 67 degrees Celsius, we can convert that into Kelvin. So how do we convert that into Kelvin? If you add 273 Kelvin to 67, you'll get the Kelvin value, which is equal to 340, right? 340 Kelvin, right? That's the absolute temperature, 340 Kelvin. And now the heat is supplied. How much of heat supplied? I denote heat supply by Q in, which is equal to 45 kilojoule. And now during this, air expands isothermally. So and then the system, that means the air inside the piston cylinder device, which is a system in this case, is converted to a different state. System goes to a different state. Now the volume has been changed because it expands, and then this state is called state 2. Now it's a change in states. So change in state means a process. So this is a process. This is a thermodynamic process. And during this, and it says expands isothermally. So that's a condition, or that's a particular specific process. That isothermal means during the process, temperature stays constant. During the process, temperature stays constant. So since the process is isothermal, we know that T2 is equal to T1, isothermal process. So it's 340 K during isothermal process. And now volume has been changed. So V2, we don't know what V2 is. And what do you think about the pressure? Now this is a isothermal expansion, and now we need to think how the piston and cylinder works when air expands. Now think about the piston is free to move. What do we mean by free to move? Free to move means piston is free to move, means that there's no friction in between the piston and the cylinder. So we assume, so our first assumption is assume piston cylinder device is frictionless. So we assume that there's no friction in between the piston and cylinder. So whenever heat is supplied to the system or air, pressure increases due to the thermodynamic process. Pressure increases and the heat, and then the air molecules expands. And when the air expands, piston moves up and adjusts to the same pressure. Piston moves up, adjusts to the same pressure, allowing the air molecules to expand. The air molecules get more freedom when heat is applied, right? So now, since it is a isothermal process, the temperature didn't increase. Temperature did not increase, but pressure also a constant. So P1 equals to P2. Okay, so it's an isothermal process, and piston is free to move. So what happened is the pressure also is the same, right? Now, we need to find determine the amount of boundary work during the process. Okay. So first, we would like to start with a boundary work. So boundary work can be related to first law of thermodynamics. If you write the first law, you can write for a closed system, delta U equals to Q minus W. Now, when I write Q minus W, this is the heat input, right? And this is net output. So this is actually net input. Let me write, it's a net input. And this is net output. So sometimes this equation is written as delta U is equal to Q in minus Q out plus W in minus W out. But in many occasions, especially in heat engines, what the desired output is the work output, right? The desired output is work output. The reason of heat engine, the existence of heat engine is to supply heat and get work output. So this is, we can write this equation, Q in minus Q out means it's net input, right? I can say net input. And then I can take this negative sign out of the parentheses and I can write minus W out minus W in. So this represents net output of work. So I can write in short terms, in short, we can write net in minus W net out. So that's the equation that I wrote first. So I just give you a clarification how this equation related to this one. Okay, so we're going to be using this during our next lessons as well for closed systems, right? So we are given how much of heat supplied. We already know this one. We are asked to find this, the net work output. To find that, we need this. So this is going to be U2 minus U1. The internal energy at state 2 minus the internal energy at state 1, right, by Q net in minus W net out. Now we need to have a method to quantify what that delta U value is, what this delta U value is. So if you look at for ideal gases, we have an equation delta U is equal to CV delta T. CV delta T. Okay. So now we can put this equation into that and we can write CV times T2 minus T1 equals Q net in minus W net out. Okay. So now what's the difference between those two? T2 minus T1. T2 is equal to T1 because it's isothermal process. So there's no internal energy change during this process. That's going to be 0. And now we get net in minus W net out, right? So you get W net out is equal to Q net in. So we get W net out is equal to 45 kilojoules. So the work output, total work output, is equal to 45 kilojoules in this case. Okay, so let's go over the problem briefly again. So what we did first is we drew a figure that represents the physics of the problem. And we want to draw that as much visual as possible. And we're going to put all the data, and we know going to put all the known data and information on the figure, which would be easier for us to see what we are looking for. So we are looking for the work output, and then we're going to start with an equation that involves what the boundary work is, and then we're going to proceed and find out what the known values are. Once we plug in all the known values, then we're going to find the unknown quantities. So the unknown quantity here will be delta U. We found that this temperature delta U is equal to Cv times temperature difference. Cv is the specific heat at constant volume. And then since T2 is equal to T1, change in internal energy is going to be 0. And then the work output is equal to net heat input, which is equal to 45 kilojoules. So that's the solution to our problem. I hope you get a better understanding of how the first law of thermodynamics is used to solve a simple thermodynamic problem, and also the understanding of what is the state, what is the thermodynamic process, and what is the isothermal processes. Once again, thank you very much for watching this video. And if you have any questions, comments, please let me know. Thank you.